right, continuing on with the solutions for our sample test for number 13, we have the derivatives of inverse trig functions. Now remember, I will give you these formulas for the derivatives of the inverse trig functions. You don't have to memorize them. But whether they write it as like sine to the -1 or arc sine, that means the same thing, inverse trig function. So arctan or tan to the -1, that would be the inverse trig function. So for inverse sine of x cubed, if it was just inverse sine x, my formula is 1 over the square root of 1 minus x squared. But I don't have just a plain x. I have an x cubed. That's my u. So I'm going to replace, normally there's an x right here. I've got to replace the x with x cubed. Replace the x with x cubed. All right, if I do that u substitution, then that's chain rule, right? So this is the derivative of the outside, and then I would be multiplying that by the derivative of the inside. So the derivative of x cubed would be 3x squared. All right, then for inverse tangent, same thing. Anything to the -2 would be -2, that thing to the -3, and then derivative of that thing. So derivative of inverse tangent, there's nothing other than just x right here, so that's just the straight formula. So it's just 1 over 1 plus x squared. So if I simplify this, when you have a power raised to a power, you multiply. So x cubed squared is going to be x to the 6th, and then we've got our 3x squared in the numerator. And then over here, it'd be perfectly fine to leave your arctan to the -3 or move it back down to the denominator to get rid of that negative exponent, whichever you prefer. All right, then for 14, we have a product. We have e to the x squared times ln x cubed plus 2. So we're going to do first times derivative of second plus second times derivative of first. So first, e to the x squared times derivative of second. Now remember that when you do the derivative of a natural log, the derivative of natural log is 1 over u times the derivative of u. So it ends up being your u value is in the denominator and the derivative of that is in the numerator. So our little shortcut has been put the original in the denominator and its derivative in the numerator. So first times derivative of second plus second times derivative of first. So the derivative of e to the anything is e to that thing times the derivative of that thing. So derivative of e to the x is e to the x. Derivative of e to the u would be e to the u times the derivative of u. So again, this is first times derivative of second plus second times derivative of first. So we could simplify that a little bit, just combining these two over that common denominator. And then you don't have to move these out in front, but you can. And we could take out, we could factor out an x e to the x as well. That would be another way of writing this, but it's perfectly fine to leave it as it is. All right, then 15, we have a log that is not a natural log. We've got a log base 5. So any log that is not a natural log, our formula for that, so like if we've got the log base a of x, the formula is 1 over x ln a. So log base a of x, it's 1 over x ln a. And since this was not just a plain x, then I'm going to use chain rule, and so I'm going to multiply by the derivative of 2x plus 3. So this would be derivative of the outside, and then this would be derivative of the inside. All right, then 2 to the x cubed, the derivative of a to the x is going to be a to the x ln a. So because this was not just a plain x, it was an x cubed, then we need to multiply by the derivative of x cubed, which is 3x squared. So again, derivative of a to the x is a to the x ln a. And because this was not a plain x, then we use chain rule and multiply by the derivative of x cubed. All right, so I definitely can move this to 1 times 2 is 2 to my numerator, but nothing else really that we can combine here. All right, and then for 16, we've got y is equal to ln secant x. So again, remember when you do derivative, the original is in the denominator and its derivative is in the numerator. So secant in the denominator, the derivative of secant is secant tangent in the numerator. Those secants will cancel out because remember you can cancel things that are being multiplied. This is secant x times tangent x. So the secants will drop each other out, and that would leave me with just tangent x. And then last, logarithmic differentiation gives us a way to take something that's very complicated, something that has a product or a quotient, and gives us a way to rewrite it, because if you'll remember, when you have the log of two things that are being multiplied, you can break those into two separate logs being added. And when you have the log of two things being divided, you can break that into separate log that's being subtracted. So in my original problem, there was no log. We're going to insert an ln on both sides. As long as what you do to one side, you do to the other side, it's a legal move. And so then we can use those properties of logarithms. All right, so we've broken this apart. Also remember, we have a property that says that if you have an exponent, you can move it out in front and make it the leading coefficient. So that's what we did here. Same thing here. We took this 3 and moved it out in front. I'm going to need to rewrite this radical with a rational exponent, and then I can move that out in front as well. So all we've done here is use the rules of logarithms to simplify this so that I don't have to do product rule and quotient rule and all of those things. All right, so now I'm ready to take the derivative. So the derivative, when we do that implicitly, you're going to do derivative like normal, but if you have a y, you're going to have to leave a dy dx in there. So the derivative of the derivative of ln x is 1 over x. The derivative of ln y would be 1 over y, and because there was a y there, we have to leave a dy dx. And then over here, I've got two things that are being multiplied. I've got 1 over x times ln x, so I'm going to need to use product rule. So I'm going to do first times derivative of second plus second times derivative of first. Now, 1 over x is x to the negative 1. So when we do the derivative of 1 over x, when we do the derivative of x to the negative 1, that's negative x to the negative 2. So first times derivative of second plus second times derivative of first. All right, then we're just going to bring that 1/2 down. And remember that when you do a log, the original is in the denominator, its derivative is in the numerator. We're going to bring that 3 down. And then for our log, the original is in the denominator, its derivative is in the numerator. So over here, I could combine my 1 over x and 1 over x and get 1 over x squared. I also could write this negative x to the negative 2. Here's my negative. But x to the negative 2 I could write as a positive x squared in the denominator. So you'll notice that these two pieces have a common denominator. I'm going to go ahead and combine them with that common denominator, and then this piece came straight down and this piece came straight down. I'm trying to get dy dx by itself, and to do that I need to get rid of this 1 over y. So I'm just going to multiply both sides by y. When I do, that drops out and I'm left with just dy dx over here, which is what I want. And then I've got y times this answer that we already had. Now this is the derivative of y in terms of x. I'm not allowed to leave a y in there, but if you remember in the very beginning, they told us what y was equal to. That was our original problem, right? So if this is what y is equal to, let's come down here and let's just replace y with the original equation, because that's what y was equal to. Now everything is in terms of x. So for our logarithmic differentiation, we're going to use our logarithm rules to break this apart to make it simpler to take the derivative. We're going to take the derivative implicitly, where if we multiply, if we do a derivative with a y in it, we leave a dy dx in there with it. And then we're going to multiply both sides by y to get dy dx by itself and replace the y with the original equation. Now, for the test, I wouldn't give you one this long because I know that's very time consuming, but I did want to give you one that had an example of what happens if you have two quantities that are being multiplied, or what happens if you have two quantities that are being divided, or what happens if you have an exponent that when you move it out in front, then you end up having a product that you have to use product rule. So I just wanted to demonstrate all of those things for you. You won't have to do all of them together, but some of those for the test.